Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at finding the area under a curve. So we're going to look at this curve y equals e to the power of negative x squared. Now what I want to do in this example is find the area under the curve between x equals 0 and x equals 1. So really I'm finding the area here, and this has many applications. It's a very important concept in mathematics. So how do I do that? Well, that's actually not easy. So one very smart guy a long time ago came up with the idea of rectangles. What we could do just to estimate it is draw rectangles. So I'm going to draw here what are called left rectangles. That means they meet the curve on the left. So it met it on the left rather than the right. So we can use these rectangles here, and they will tell us a bit about the area under the curve. So the distance here is 1, and there are 4 rectangles, so the distance of each of these is going to be 1 over 4 or 0.25. So this first rectangle, I'm going to call it rectangle 1, it's going to be 0.25 in width, and then its height is 1. So it's just 0.25 square units. Now what about the second rectangle? Well, again, its width is 0.25. and its height is whatever the function is at this point. So that'll be e to the minus 0.25 squared. Similarly, the third rectangle, sorry, that was the second. The third rectangle once again has width 0.25. Now its height will be whatever the y value is at this point. So it will be e to the minus 0.5 squared. And then for the fourth rectangle, you guessed it, once again, 0.25 is its width, and its height will be e to the minus 0.75 squared. So it turns out if we put this on our calculator, we get the area being approximately 0.822. Now it turns out the actual area is about 0.74682. So our answer was off by quite a bit actually. Now we can see that our answer was always going to be bigger than the true area because these rectangles were larger. The problem is that we actually didn't use enough rectangles. Heaps of rectangles to be accurate. If I wanted to be fully accurate, what I would do is have like a rectangle here, a rectangle here, a rectangle here, a rectangle here, and so on. So basically we want the number of rectangles to get larger and larger, and the width of each of those rectangles will get smaller. So it turns out that if you use more and more rectangles and the width of those rectangles gets smaller and smaller, then the combined area of all of those rectangles actually approaches an antiderivative. For me, this is one of the most amazing things in maths. So if I want to actually find the area under the curve of a function, let's call it fx, what we do is integrate it, because that will actually give us the exact area. So we need to integrate it between two values. So we just call them a and b. So you need to find the area between the specific values of x. So here our values were 0 and 1. You always put the lower value down the bottom when you're writing this. So a is less than b. Now it turns out, as I said, the area converges to an antiderivative. This is called the fundamental theorem of calculus. The integral of fx dx between these two values is equal to the antiderivative evaluated at the larger value minus the antiderivative at the smaller value. So when we're doing these are called definite integrals. Your answer will actually just be one number, and that number is the area under the curve between these two values. Now notice when we're doing definite integrals, we don't need to worry about plus c's because they would cancel out. I'd have a plus c here and a plus c there, c minus c, they would cancel out. You only need to add the plus c when you're doing indefinite integrals, which doesn't have the numbers here. So this is how we find the area under the curve. Let's look at a few examples. So let's say I want to find the area under the curve of y equals x squared between x equals 1 and x equals 4. So to find the exact area, rather than needing to do all the rectangles, we can just go the integral from 1 to 4 of x squared with respect to x. So we know the antiderivative of x squared is just x cubed on 3. Now I don't need to add a c here because of the numbers. This is a definite integral. What I do is evaluate it at 1 and 4. So if x equals 4, x cubed on 3, so 4 cubed on 3 is 64 on 3, and then I minus the function evaluated at 1. So that'll just be 1 on 3. I get 64 over 3 minus 1 over 3, 21 units squared. Now let's look at finding the area under the curve of y equals 9x minus x cubed between these values, which is actually a bit more complicated. So the reason this one's a bit more complicated is its graph looks like this. It actually spends some time under the x-axis. So if I were just to go and calculate the area like normal, the problem is this. This area here would actually be negative when you performed the integral. Negative area just means it's below the x-axis, whereas this area here would be positive. It turns out for this particular function, these two are the same area. So if I just integrate this one from -3 to 3, I will get 0. These two areas will cancel each other out. That won't really tell me much about the true area. So what I'm going to do is integrate each region separately. So from -3 to 0, that's the part where the area is negative. I'm going to integrate the function. Now, because that area is negative, I'm just going to put a negative sign out there. This is negative. Putting the negative sign out there makes it positive. I want the area to be positive. And then I'm going to add the area of the next region. So once again, we're integrating the same function, this time between 3 and 0. So let's perform these separately. So over here for this one, we have our negative out the front. So we're going to increase the power by 1, divide by the new power, increase the power by 1, divide by the new power. So we need to evaluate that at -3 and 0. That's what the fundamental theorem of calculus says. And then similarly over here, we're going to increase power by 1. We're going to get the exact same antiderivative, and this time we're going to evaluate it at 0 and 3. All right, let's first calculate this one. So if x is equal to 0, this thing just equals 0. So we have minus 0. Now, if x is -3, we get 20.25. So we evaluate the function at 0 and subtract the function there evaluated at -3. So you can see this would have been -20.25. That's why we put the negative there. And over here, it's probably no surprise we're going to get positive 20.25 when this function is evaluated at 3, and when it's evaluated at 0, we just get 0. So putting these numbers together, -20.25 plus 20.25, we get a final area of 40.5 units squared, which is positive. All right, let's now look at an example for the area between two curves. So we can use what we know about the area under the curve to find the area between two curves. So we're going to find the area between y equals 2x squared and y equals 3 minus x squared. So when you're calculating the area between two curves, it might be helpful to graph them. You might use a graphing tool like GeoGebra, Symbolab, whatever. So when we're asked to calculate the area between the two curves, I'm calculating this area in here. Now, the good news is when you're calculating the area between two curves, you don't need to worry about whether the curves are above or below the x-axis. What you do need to worry about is making sure you get the correct one on top and finding the points of intersection. So what we're really doing here is we're finding the area under the red curve, which is the whole lot, this whole area here, and we're subtracting the area under the blue curve, which is this part here. So this whole area under the red curve, subtract the area under the blue curve, leaves this, the area between the two curves. So what I'm going to do to find that, it's just going to be the integral of the one on top must go first, minus the one on the bottom, and we're integrating that between the 2 points of intersection here, -1 and 1. So, of course, we can make this a bit easier on ourselves. -x squared minus 2x squared just becomes -3x squared. So if you don't get the right one on top that's listed first, you might get a negative area. Of course, we want the answer to be positive. So integrating this, integral of 3 is 3x, integral of 3x squared, increase the power by 1, divide by the new power. Of course, the 3's cancel out. It's just 3x minus x cubed evaluated between -1 and 1. So substituting 1 into this function, I get 3 minus 1. Substituting -1 into the function, I get -3 plus 1. So I get 2 subtract -2, which is 4 units squared. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.